All right, AI SL2. We've reached the end of kind of all of it. What a long, strange trip it's been, you guys. Today we're talking about the integration chapter, and these are the closure notes of everything that could come up on a test. First up, we started talking about definite integrals. Definite integrals, the notation is this big curly Q from A to B of a function with respect to x. Remember that represents the area underneath a function. So a little visual here is it's the area with respect to the x-axis underneath a curve. That's what this whole thing would represent. All of this is that. It's the area of all this. In the beginning, there was polygons. There were straight sides where we're like, well, we could break it up into triangles and rectangles and use all our geometry knowledge. Cool, that might come up, but very quickly a lot of that stuff went away and we just started using curves. That says curved, not curd. I apologize. Here, we'll fix it, guys. I got it. Curved. Well, yeah, that's not great. Anyway, if it's curved, we have to use a calculator for it. So one of the main ways we did it was with fnint. You can find that by hitting the math button and then scrolling up a little bit. That one's super great if you have a nice menu on the TI-84 Plus, but it works on 83 as well. You just have to punch in things in a certain order. I think the order is it's backwards of what it should be. It's the function, and then you put x because that's respect to x, and then it's the lower bound, and then the upper bound. The other way we did it is that we graphed certain functions and then hit the second and then calculate button and scroll down to this guy right here. That's where you can punch in your start and your stop, and then it shades the area underneath the curve and tells you what that area is. So two powerhouse ways to find the area under a curve right there. Then we learned by far the most confusing and probably unnecessary thing in the chapter, which is the trapezoid rule, where you can take the area underneath a curve and split it up into a bunch of trapezoids. So you're still finding, the area under a curve using this definite integral, but it's like this is a big trapezoid formula. The way it works is the whole interval you're going over is b minus a, and then you're splitting it up into n chunks. Those are the heights of your trapezoids. Then all the bases are like the first and last, but then everything in between first and last gets counted twice. So that's why there's a 2 there. Next up, antiderivatives. We still looked at like a definite integral. If you integrate a definite integral like f of t, this is capital F of x minus capital F of a. I think that information got a little lost in the chapter, that it's like you take the antiderivative, that's what that is, the antiderivative, and then you plug in x into the antiderivative, and you plug in a, and then you subtract the 2. That's how you find the definite integral. Remember the relationship between capital F and lowercase f. If you're starting with capital F and going this direction, you're differentiating, which is taking the derivative of. So here, this is the antiderivative, and this is the derivative. The whole purpose of this chapter, one of the big points, is that you can start with a derivative and get back to the original starting thing, which is called the antiderivative, and we do that through integration. The opposite of integration is differentiation. It depends on which way you're trying to go and what you're trying to get. Indefinite integrals. Notice there are no starts and stops on the bottom. That's just a general antiderivative. So you take your antiderivative, but then you got to put this guy on the end. This is your constant of integration. Remember, the constant of integration is just any real number. It can be decimals, it can be fractions, it can be negatives, whatever. But in general, we just call it lowercase c. The reverse power rule for finding an antiderivative, if you start with an ax to the n, then the antiderivative is bumping the power up by 1. That's the whole m plus 1 up here. But then you have to divide by m plus 1 on the bottom as well. And as always, don't forget your plus c, constant of integration. We did a little bit of applications at the end. Most of them seem to have to do with like the graph and finding the original function. So a lot of times they gave you a derivative, so given a derivative, and asked you to find the original function. You take your antiderivative, but then usually you had to plug in a coordinate to find your exact c value, so you're not leaving a plus c on the end. The other very weak real-world stuff that they did in that chapter was cost problems, like the original function being cost of x, and then the derivative of cost being called marginal cost. So marginal cost is a derivative. If you want to get back to the cost function, take the antiderivative of the marginal cost. All right, you guys, I think that's all I got. Good luck with the review. Please come ask me questions, or if I need to show you any, go over any calculator steps, please let me know.